Sí, buenas tardes, soy el capitán de navío Pérez Villalonga, director de la Escuela Técnica Superior de Ingenieros de Armas Navales de la Armada. Nuevamente les doy la bienvenida a este ciclo de conferencias sobre ingeniería de sistemas y hoy vamos a tener la oportunidad de escuchar a Mr. Gary Smith y nos hablará sobre System Thinking, la importancia del pensamiento sistémico en el desarrollo de sistemas complejos. Como en otras ocasiones, cedo la palabra a Bernardo Delicado de la Asociación Española de Ingeniería de Sistemas, quien presentará el ponente ya en inglés para todos ustedes. Muchas gracias por su asistencia.
Gracias, comandante. Buenas tardes a todos desde España. Let me switch to English language for the benefit of our prestigious speaker. My name is Bernardo Delicado. I'm the facilitator of this conference program on behalf of INCOSI. Welcome, everyone. Thank you, Gary Smith, our guest speaker today. Also, thank you all the participants from Spain, Spanish-speaking countries, and worldwide. Once again, let me say that we would not be here without the Spanish Navy and INCOSI to make happen this conference program. Let's all show our appreciation for them. System engineering could not exist without system thinking. The sense of system thinking is in seeing the world in a particular way, seeing the wholeness instead of parts, because how you see things affects the way you approach situations or undertake a specific engineering task. The practice of system engineering is a balance between systemic and systematic aspects. Systemic aspect, taking advantage of system thinking, means thinking about the whole system, its context, and stakeholders. On the other hand, systematic aspect means following a structured approach to the realization of the system. Some people seem to have a natural talent for system thinking, just as some have natural talent to play piano. But most people find it rather awkward and difficult at first. That is why our conference today is about system thinking. Our presentation today is realizing the power of system thinking in engineering. It is time for a grand leap in our system engineering capability. Our programs and projects are by necessity becoming increasingly complex due to the interconnectedness of everything and the potential that this interconnectedness and unleashes. Complexity requires and demands greater appreciation. Complexity brings with it the potential for powerful solutions, and yet at the same time powerful problems. In our system engineering, our body of knowledge has evolved heuristically to help our profession make sense of and deal with such problems. INCOSI, in collaboration with International Society for the System Science, has been working to create a holistic framework for system science. Its purpose is to provide the means to organize the pursuit and practice of system knowledge as a learning system. System engineering and system thinking experience has played a vital role in shaping the architecture of this framework. And when these heuristics are placed in the context of the whole, new insights and connections emerge. Since When you place heuristics in the context of the whole, the system science framework, it gives a deeper meaning. Heuristics do not stand alone and become part of a greater system that will empower our engineering based on scientific principles. As I said earlier, Gary Smith is our guest speaker today. Gary Smith is an INCOSE ESEP, a senior expert system engineer at Airbus Defence and Space, where he is engaged in the system of system engineering and organizational transformation program. There, he is the Vice President of System Practice for the International Society for System Science and is the INCOSE Liaison and Relationship Manager. He is the Senior Editor for the System Foundation session of the System Engineering Body of Knowledge. Gary has applied system thinking to understand the nature of disease in living systems and these functions in organizations. With Brigitte Daniel Allegro, proposed the System Tree as a framework for systemic concepts. This incorporates the attitudes of the system thinker and the concepts they think about when seeking to understand and engage in systems. Personally speaking, I met Gary working in Airbus a long time ago as part of the corporate community working on system engineering involved in INCOSE. I can only say that Gary is a privileged mind in system thinking and system science. And finally, please use the chat in Teams for your questions. We will use the last 10 minutes for your question and answers. We will try to address some of them. Just now time for our guest speaker. I leave in the capable hands of Gary during the next 40 minutes. I give the floor to Gary. Please, Gary.
That's very kind of you. Thank you, Bernardo. And thank you for the invitation to be able to present. So can you see my screen? Is it coming through?
Yeah.
Okay, great. Yeah. So the title is Realizing the Power of Systems Thinking in Engineering. As Bernard said, in terms of the systematic and although it's also the systemic aspects in systems engineering. This is the contents of the overall talk, and what I wanted to do was to split it into three parts, really. The first part is looking at the challenges that we face in our projects, our programs, and also our everyday lives. I'll then go on to explain some essentials about system science, its foundations, and how systems thinking is integrated into that overall framework. And then I will then go on to really the main part, the juicy part, really, which is where we explain how the science and systems thinking can be used to empower our practice. But in order to be able to do that, I need to go through these parts first in order to give you the context and the concepts so that this part really makes sense. So that's the overall structure. I'll also be referring to the Kinofin framework, which some of you may have come across. This has been very useful in bringing together the overall system science and also for providing a great way of making sense of the chaotic, the complex, the complicated, and the clear. So I'll make reference to that a few times. So just very quickly with my background, Originally I was a chemist, and my background in chemistry has been influential in my thinking about systems and in my thinking about system science. As it was mentioned in the introduction, I've applied systems thinking and systems design concepts, looking at biosystem complexity in my spare time, and I've published a number of papers on things like cancer and inflammation and sepsis, and I've also contributed to a recent paper on COVID as well. So this is one of the things that I do to help me really with my systems thinking, because this forces you to systems think when you're working in a domain which is not familiar to you. In my background at Airbus, I have been an architect for border security systems, and again, there's been some very interesting parallels between border security in the engineering context and looking at essentially biosystem security in biological systems. There's a lot of parallels. And I'll talk a little bit about parallels and the power of analogy as we go through the talk. It's been mentioned that I have some associations with INCOSE and also the International Society for System Sciences, and Bridget and I did some work together on something which we called the systems tree. So these are the concepts that the systems thinker thinks about, and these are the, if you like, the attitudes of the systems thinker. And this is one of my bookshelves at home, and I think this tells you a little bit about my background as well. There's a mix of science, the Open University, which has been very influential, books on philosophy and psychology. I also do a lot of role playing. Well, I have done role playing in the past, things like Dungeons and Dragons. I read a lot of science fiction. And also things like Harry Potter and Terry Pratchett and stuff like that. So yeah, I'm a bit of a strange person, I guess. This is a slide that Bridget and I used before. So systems thinking is what you have to do when you're faced with the inexplicable, the unaccountable, unexplainable. When things just don't make sense, this is when you have to apply systems thinking. And Captain Jarrow is Captain Jack Sparrow from the Pirates of the Caribbean is one of our heroes, because he says the problem is not the problem is your attitude about the problem. Do you understand? And really, when you do systems thinking, what you're doing is you're changing the way that you think. That's what systems thinking does. And when you do that, you can get new understanding. So I'm now going to go into the challenges, and just a reminder, there are some really big global challenges that are facing us at the moment. Climate change, pandemics, all sorts of things that are arising because our world is becoming more and more complicated, and we've moved into a new geological age called the Anthropocene, where humankind is actually changing the very geology of our planet. This little diagram here from Bernard and Ray is nice, because they say, I supply complexity and confusion, but I can organize exploration of it as a learning system. There is far too much to know, but one of the things that we're trying to do with system science is to essentially create a framework for all of our system knowledge. So one of the things we did with the ISSS a few years ago is we had a workshop with a very diverse group of people, and we asked them in that session to consider what were the key things that they considered to be non-systemic. What were the features of being non-systemic? And we've now labelled these as essentially systemic pathologies, and these were the clusters. So we've got around this cluster: isolation, pain, sadness, no sense of nature, lack of information, knowledge and appreciation, no vision of the future situation. Here we've got confusion in complexity, not seeing the connection flow of causality, having a perspective gap, limited choices, resource and energy gap, going in the wrong direction, unintended consequences and not seeing the big picture. So these are the things that tend to happen when you're not systems thinking or when you're not being systemic. And these are the things that we see not just in our everyday lives, but also in our programs and our projects. And when we look at the impact of complexity and confusion in projects, there's some great work from the Standish Group with their chaos reports. And they show that there is a strong correlation with success challenged and failed in terms of complexity. So very complex projects, only 15% of them are successful, truly successful, you know, time, cost and quality. 57% of them have major issues with you know, not achieving the full scope of the project, and 28% of them are actually cancelled because they realise that the projects, you know, they just cannot achieve any meaningful success. So they do the right thing and they cancel them. And when we look at the reason why projects and programs fail, these are some of the main issues that came out of that, and these were reported by project managers attending training. So 36% related to poor organisation and project management practices, 20% to poorly defined or missing project objectives, and 15% related to ineffective project planning. So this is really the impact of complexity and confusion in these projects. Another factor is the relationship between the systems engineers and the project management discipline. There was some great work done by INCOSE in combination with PMI and MIT, and they did a survey of program managers and chief engineers, and one of the biggest factors for what they called tension between the two disciplines was a lack of integrated planning. This was the #1 root cause of issues, and it's a major factor why complex project programs fail, because the relationship between systems engineering and project management is so important. So if these two disciplines aren't working together effectively, this leads to, you know, major challenges. Another great report from that alliance between the three organisations is the Guide to Lean Enablers for Managing Engineering Programmes. And this really is a must-read publication for any programme managers and systems engineers who are working in complexity. So this multiple cause and effects diagram shows ultimately the pathways to reactive programme execution and firefighting. Is it not just really insufficient appreciation of the required complexity and the organisation necessary to deal with it? And one of the things that is important is what takes place right at the very beginning in terms of the acquisition and the contracting processes. If these things aren't supporting sufficient programme planning, then firefighting will result. And there's this statement from Alexander Bogdanov in 1917, who has been very, very influential in system science and the development of system science. And he said, "A disordered whole is practically less than the sum of its parts." And I think that's a really great statement. Now, if we look at the impact of technical debt and the insufficient appreciation of complexity prior to project startup, which some associate with contract award, if you don't do enough investigation of the problem and the solution and enough preparation up front, you will end up with an effort curve which looks like this. And this is essentially not doing the right things at the right time. This is work that's come from the INCOSE PMSE Integration Working Group, and this is a great piece of work. You know, the ideal profile is something that looks more like this, which is where you have a really good appreciation of the problem and the solution. You formulate, for instance, your product breakdown structure, your work breakdown structure. You know what it is that you have to do before you start doing the work. If you don't do that, you end up with a curve that looks like this, which is a very painful experience on complex projects. And one reason for this is what I call a terrible divide in understanding, where you have a proposal phase and you have a team who are responsible for making the proposal. Their mission is accomplished when the proposal is completed, and then a brand new team comes into play after the contract, and the responsibility is now under the project management. And because you've not sufficiently prepared with your understanding, you have a cost, time, quality triangle which looks like this. But then when you start the program, it actually turns out to be much more complex and much more difficult than you thought. And the scope is a lot bigger. And because the budgets have already been established, it's very, very difficult to get back on track. So I think, again, this is one of the problems that we face. And systems engineering really matters because it addresses complexity when it is done at the right time in the right way. I had a conversation with Kevin Forsberg a few years ago, who was really one of the leaders in the establishment of INCOSE, and he said to me that systems engineering is really about clearing away the fog and making things clear, and I think that's really important. When we look at the amount of effort which is spent on systems engineering in NASA, there is a close correlation between the level of effort which is spent and the level of program overrun. So when we're talking about 3.0 here, we're talking about 300% cost overrun. And in this particular case, there was no effort applied on systems engineering. The sweet spot seems to be somewhere around 12 to 16% of effort on a program being spent on systems engineering. Some more work which has come out of the INCOSE SEPM integration working group has been using COSISMO as a way of looking at the cost of the assumptions that are made prior to contract. And the ones in red are the assumptions that were made prior to contract, and the ones in blue are the reality of the situation once the program has started. So here, the requirements understanding at contract was considered to be 0.77, which was high, but actually it turned out to be low. Architectural understanding was considered to be high, but it turned out to be low. And when you multiply up all of these factors, what it essentially means is that instead of you needing, let's say, 100 hours for systems engineering, you needed 533 hours. And that escalates across the whole of the program. So in this particular program, which was a real program, the cost increase was 500% of the overall budget as a result of these assumptions that were made, which turned out to be false. So that's one of the reasons why systems engineering and systems thinking is so important right at the very beginning. So now I'm going to go on to system science and the dawn of what I'm calling applied systemics. So I'm going to go through what is system science, what are the foundations, and how systems thinking heuristics are integrated into that. And I'll make reference to many different works. I think it's important for me to also explain that what I'm explaining here is not just my work. It's been the work of collaboration across many people. So what's this system science all about? So Richard Beasley, I had his permission to say this. So he wears a badge, and on his badge, so Richard's an INCOSE ESEF as well, and on his badge he says systems are everywhere and everything. And really, this is what this system science is about. It's about all of these systems. It's about these cosmological systems, the biological systems, the human civilization systems, the social systems, the ecosystems. So systems are everywhere and everything. And the idea of system science is it would be a systematic and systemic enterprise that discovers, develops and organizes system knowledge in the form of testable explanations and predictions about the universe. And the reason why we have the potential for a system science is because there are general concepts, patterns, principles and assets that are truly transdisciplinary and go across all of the different types of subjects. It goes across physics, chemistry, biology, sociology, and even politics and economics. There are certain principles and concepts which span all of these different types of systems. And when you look at the emergence of these systems in these different system levels, we can see that there is a process, a natural process of integration, emergence, and diversification, which results in these levels and ever greater complexity. So system science is about all of this stuff. And there is a grand pattern which we experience across all of these systems, and I can explain it in the context of Kinofin, which was the work of David Snowden and others, but I can also relate this to our engineering experience as well. So in the center of the model, we have nature and society as a greater whole, and this is both the beginning and the end in terms of data. From data we derive information, we make observations, we have ideas, and this is where we work out why. And in the Kinofin model, this is referred to as the domain of the perceived chaotic. When we encounter this area, we identify illuminating information, theories, and concepts, and we build frameworks. And these frameworks are our knowledge, our architectures, and this is where we appreciate complexity. This is where we work out what. And then with our architectures, our structures, and our patterns, these then provide the enabling constraints for our designs. And this is where we apply our principles. And this is where we deal with and master the complicated through our designs, and we bring together power and forces to manipulate energy and mass, create our assets through realization. And when these assets are then applied in nature and society, sometimes we get surprises, nice surprises, but also surprises that we weren't expecting. And that brings with it new opportunities and the potential for new ideas and new frameworks and new principles. And when we consider that in the context of the scientific method, we can see again the same pattern applicable to science, and the engagement in terms of principles and the creation of our technologies and our systems. And over here we have the ideas, the theories, the hypotheses, which we use to build our frameworks, our architectures. And then within those architectures, we then apply our principles to create our systems and our solutions. So what I'm now going to introduce you to is the idea of transformational powers. So there are 9 powers, and the use of these powers will become more clear as we go through the presentation. But there are 9 powers, and these powers over here are, let's say, more feeling, and over here we have powers which are more tangible. So these are the tangible powers. So these are, we have the power of spirit, philosophy, and theory over here, and these are powers that we engage with when we're conceptualizing and architecting. We then go into the technical, the action potential, which is where we're using that power when we do design. When we're implementing our designs, we make decisions, and there is a power of design aesthetics, and design aesthetics then has an impact on social, and we also have political as a power, which is used essentially to turn all of these wheels around. So conceptualizing, again, architecting, designing, and realizing. Another thing I'm going to introduce you to is the idea of fit, form, and function, which many of you will have heard of before. And again, there are reasons why I'm showing you these things. So form, in form, we're dealing with topics like the system identity, the characteristics, and its behavior, and these are the limits of the system self-control, and these are the powers that are applicable in this particular area. The powers to transform form, essentially. Here we have a function, and this is where we consider the system place, its purpose, and its life cycle. So again, classically relating to the criterion that is met when the part system performs its stated purpose effectively and reliability. These are the powers that are at play here, and then there's the wider space, the context within which that system is playing its part, and this is the possibility space, the situational context, the stakeholder perspective. So this is where the fitness of the system is judged by the external context, and here we're dealing with the power of spirit, social, and design aesthetics. I think, yeah, so yeah, I'll leave it at that. I don't want to talk too much about that because I'm just trying to slowly build up a picture. Now, when we take the concepts of form, function, and fit, we have two knowledge areas related to this: identity and behavior. So the togetherness of things and the relationship of things, this is the domain of form, and these are the system concepts that we use when we observe and we talk about identity and behavior, things like structure, components, boundaries, boundedness. And here we're talking about activity, dynamics, influences, interactions. These are the concepts related to cycles and capability. These are the concepts related to value and consciousness. So here we're talking about the experience of things and the value of things. So, and the concepts we're using here are things like perspective, judgment, circumstances. When we're talking about consciousness, we're talking about awareness, understanding, empathy, comprehension, and what you can see is on this matrix, which shows the 5 let's say phases across the top. What we do on this matrix is we show the intersection of these stages with these knowledge categories, and now what we do is we place the powers and the problems, the pathologies, onto this framework. So what you can see is, for instance, the power of the technical can be used to help resolve confusion and complexity. The power of technical can help to resolve the issue of not seeing the connection flow of causality, and the power of technical can also help to resolve issues of limited choices. And over here we have the assets which are created when we apply these kinds of principles, and these principles would be derived from these theories. So the idea of this framework is we will able to essentially plug in all of our knowledge about systems within this framework as an organized whole. And using the framework, you would be able to access this knowledge in the pursuit of, for instance, systems engineering processes. And that's what I'll be talking about in the final section. There's a little bit more theory necessary for us to get there first. So what I've done is I've taken this framework, and what we've done is we've mapped in many frameworks, heuristic frameworks of systems thinking. So for instance, systems thinking made simple, the ways of the systems thinker, the habits of the systems thinker is a particularly good one. I'll be using that as we go through. But what we've done is we've taken all of these heuristics and we've placed them on the intersections between the problems and the powers. And here's one example of a heuristic from the Waters Foundation, the habits of the systems thinker. So, they have these nice diagrams, these pictures, and this one is recognizes that a system structure generates its behavior. And this is one of the heuristics which sits up here on this particular pathway from here to the engagement of this power. Because I'm guessing the presentation is going to be shared with everybody, and I've included this just to give you access to all of these different works on systems thinking and where you can get them from. Now, when we look at the pathways from the problems to the powers, we've now labeled the pathways to give them meaning. So confusion and complexity, going to the power of theory, you generate hypotheses. When you go into the power of the technical, you're exploring potential. When you're not seeing the connection flow of causality, you make the dynamics explicit, or you plan ahead to engage the political power. If you have limited choices, you develop technologies, or you extend what is possible with action potential. So you get the idea. These are pathways to powers to essentially get you away from the problems that you're experiencing. Okay. Now, the other thing to bear in mind is, as well as the positive pathways and positive systems thinking, there are also some shadow traps in thinking and attitude. Bridget and I did some work exploring these in a booklet we did, exploring the branches of the systems landscape. So we considered these to be unfounded concepts because really we had the opinion that nothing was truly useless. And also there's no such thing as nothing, because even nothing is a concept. And these are some of the traps in thinking that you experience when you get lost in complexity. The other thing I'm going to make reference to is personality traits. Because these personality traits have a big influence on systems thinking capability and where that systems thinking capability is applied. I'm not sure if you're all familiar with Myers-Briggs, but there's this extroversion, introversion, sensing, intuition, thinking and feeling, judging and perceiving, and these are traits in terms of personality, in terms of tendencies, in terms of your personal preferences. So some people are more introverted, some people are more extroverted, and this has an influence on the traits that you exhibit when you're working in a team. And what becomes apparent is that this variety that we see in our personality traits is actually all part of the way that we've developed as a society and as a culture and as individuals to better work as teams to deal with complexity. And again, that will become apparent as we go through. So I'm now going to get into the main meat. I'm going to go into the technical management aspects, the conceptualization, the architecture design, and the realization and sustainment. So technical management, just as a reminder, in the INCOSE handbook, there's a section 5 on technical management processes, and these are really important. We tend to overlook them perhaps a little, and focus more on the technical processes, the processes of, for instance, architecture, design, integration, verification, etc. But technical management is a key capability that we need in order to deal with complexity. And it really provides, I would say, let's say, the bridge between traditional project management and systems engineering. It really does. It's the vehicle for integrating those two different disciplines. Bud Lawson, who was really influential on me, he was one of the key authors of the ISO standards, and very active in systems engineering. And he explained this paradigm for thinking and acting, which integrates OODA, observe, orient, decide, and act, and the plan, do, check, act loops. So when you bring these two together and you integrate them, this gives you, and when you apply it, this really gives you the capability for continuous situational management. And this is something that has to be done by technical management throughout the development of programs. This really does, when you apply it, it makes you strategic, agile, lean, and responsive. And this is really the essence of technical management. I'm also going to, I think I won't talk about this very much because this you know, you can look at this at your leisure, but here we have the categories, the knowledge concepts, the potential leverage points from Donella Meadows, and some questions that can help you, which are based on these concepts, and they can help you to identify leverage points for making changes in systems or for actually establishing new systems. And down here we have the ones which Donella said were the greatest leverage potential, and here we have the one which has the lowest source of leverage for potential. And one of the reasons for this is from John Gall. He said that all established systems resist change. And when you try and change these things, the system essentially hits back and things happen that you weren't expecting. The system is resistant. So I'm now going to conceptualizing. So conceptualizing is what you do when you're attempting to make sense of a situation. By seeing the situation from a diversity of viewpoints, you will enrich your comprehension. And when you're conceptualizing, these are the powers that are coming into play. These are the roles, the traits that are useful when you're conceptualizing. And here's some of the heuristics from the Waters Foundation related to these traits. So the thinker makes meaningful connections within and between systems, and the champion considers how mental models affect current reality and the future. And when you're conceptualizing, you draw on the power of or the utilization of analogy, metaphor, and anomaly when you're doing this conceptualization. So you gather data, you try to make sense of it, you formulate the big picture, and you validate impressions with experts and stakeholders. And when conceptualizing, these are the pathways that I showed you earlier, the ones in green. So these are the positive pathways from these problems. These are the heuristics that are being engaged. These are the pathologies in grey. In the red, we have negative pathways. So these negative pathways represent either the abuse of power or the utilization of power, you know, without I guess thinking, which serve to sustain these pathologies. So let's just look at this one of the top end, for instance. So no vision of the future situation. This is addressed through the pathway give voice to future possibilities, and this is why considers how mental models affects current reality in the future is supportive of this. The systems engineering processes which are at play in this area are lifecycle model management and acquisition. So these processes are supporting potentially both the forward pathway and the backward pathway. And the backward pathway is reluctance to change to retain the establishment. Here we've got stakeholder needs and requirements definition, which is coming from a lack of information, knowledge and appreciation. So stakeholder needs and requirements definition is supporting the pathway of engaging stakeholders. But there's a negative pathway, which is manipulation of relationships to blame the other, a subgroup or alien. So this is where we see how the systems engineering processes can be supported in this overall big picture of conceptualizing. And these are the four main traits which are useful in doing conceptualization. So when we talk about realizing the power of systems thinking in engineering, this is what we're really talking about. it's the processes, it's the thinking, it's the understanding of the pathways, both forward and backwards, and the roles, and the types of people which are helpful to unlock that power when conceptualizing. I hope that makes sense. This is architecting. So architecting is what you do when you are attempting to appreciate the complexity of systems in their situational context. And here's some, if you like, heuristics related to architecting. Yeah, taking into account multiple perspectives, relating the features of the system to the stakeholder needs, organizing the concepts and the components, and establishing the principles for design. And again, these are some of the heuristics which are useful. These are the primary powers and the players that are at play when architecting. So a similar kind of diagram. But what's really interesting for me when I was putting this together is what you start to see in terms of the emerging connections which you weren't able to see before, and also potentially gaps in our processes. So in our processes, you know, we don't have processes for essentially changing your mind or opening your mind, and maybe there's a place here for imagining and dreaming and even meditating. Because these are things that are helpful when you're in this particular space, and when you need to consider an issue fully and resist the urge to come to quick conclusions, and when you need to change your perspectives to increase your understanding. Here we've got observes how elements within systems change over time, generating patterns and trends. So this is really useful for planning ahead and in your measurement management. And your life cycle management, you know, and here we've got, again, recognizes that a system structure generates its behavior. So this is useful in systems analysis and in requirements definition. So I'll move on. Designing what you do is what you do when you're working out how something needs to be done in the context of the systems you're engaging with. Again, these are the roles and the powers that are coming into play. Here's some of the heuristics again. Uses understanding of system structure to identify possible leverage points, and that information I provided earlier in terms of the, you know, Donella Meadows and the leverage points she identified, and the categories and the concepts which are useful for identifying leverage. Recognizes the impact of time delays when exploring cause and effect relationships. This is important for the inspector. The craftsman surfaces and tests assumptions. The doer pays attention to accumulations and their rates of change. So again, all of these roles and powers are at play, and some, if you like, wisdom related to this particular domain of designing. The greater the complexity of the system, the greater the number of trade-offs that will need to be made. The value of the system is proportional to its benefits divided by its complicatedness. So the key message really here is, you know, we need to appreciate complexity. Complexity is not necessarily bad. If it wasn't for complexity, we wouldn't exist. You know, systems are by their nature complex, but what we should be doing as engineers is we should be appreciating that complexity and trying to make the systems that we create less complicated, trying to make them only as complicated as is necessary. And the viability of the system and the diversity of the components are directly related. That's also really important to understand. So this is the diagram related to designing. Again, we'll just look at a couple of these. So not seeing the connection flow of causality. We can make the dynamics explicit through the power of the technical, and we can avoid getting lost in the data when we do our systems analysis. Infrastructure management is really important when we're seeking efficiency and making sure that we're doing our part for the whole. We extend what is possible to address limited choices through our implementations, and we need to avoid firefighting. And in our decision management, we need to steer the way, the right time, the right way, and we need to avoid the issue of leaders escaping accountability for the wrong decisions, and making sure that we learn from any mistakes that we make. This is the situation on sustaining and realizing. So sustaining is maintaining in the context of business as usual. Things work, they obviously work this way, and you probably want to keep it working. And there's the adage, if it isn't broken, then don't fix it. But we need to take time to assess performance. Don't ignore feedback that things are not working. We need to remember that established systems will resist change, even when the time for change has come. You know, this is one of the things that we as systems engineers need to address. These are the primary powers and the players at play. We need to remember that we're all part of one big system called nature. We're actually already well beyond the limits of the sustainable capabilities of our planet. We can work together to create health, well-being, security and happiness, but only if we all take the system's perspective. And this is the overall situation for sustaining and realizing. And we've got things like seeks to understand the big picture, which is important in our knowledge management and the development of knowledge, and being wise to systemness. One of the pathologies that is at play down here is the tribal and silo behavior that we sometimes see. And as systems engineers, this is something that we have to address to ensure that everybody is actually working together at the right time in the right way. We have identifies the circular nature of complex cause and effect relationships. This is at play here in this particular space. Considers the long-term and short-term and unintended consequences of actions. So again, this has a place for verification and quality assurance. And down here we have checked results and changes actions if needed. So this is related to things like maintenance and quality management. Integration as a process has a big role to play here, seeking the wholeness of the system. When we have unintended consequences, we need to learn from our mistakes and we need to adapt and improve. So what I'm overall trying to do here is I'm trying to show you how the various pathways, both negative and positive, the pathologies, the roles and the processes can all come together as essentially a system for realizing and sustaining. Yeah, incorporating not just the technical processes, but the processes that support the overall enterprise, the project management orientated, technical management orientated processes. So all of these things need to come together as an overall system, and the systems engineers and the technical managers have a big role to play in ensuring that these systems and these parts all come together as a whole. Because when we're all systems thinking together, this really does greatly empower engineering. You know, so bringing together all of these roles in all of these different contexts of working out why, working out what, working out how, and establishing our common wisdom. You know, we all have a role to play in that, and it's only by working as a team that we really realize the power of systems engineering and systems thinking. So I hope that I've managed to keep reasonably in time, and I appreciate that there was a huge amount of slides there. I felt it was necessary to give you that overall story of the problems we face, the science that is emerging, and how that science has a relevance directly in our engineering processes. If you would like to know more or contribute to the development of system science, then I'm very happy to correspond. This is my email. And really there is far too much to know, but we might be able to create a framework for it all. And this is one of the things that I'm hoping to do with this systems engineering body of knowledge, to capture all of the essentials and to make explicit the tools, the methods and the practices that can support our engineering.
Thank you, Gary, for your great presentation. Very interesting. You know, we have a little time remaining, but we will have the opportunity to pose some questions. Please use the chat. Here we have a question, Gary, related to when talking about system engineering and project management integration, which are, from your point of view, the necessary actions to smoothly integrate both disciplines in an organization?
Well, I think that what we're finding from our engagement with project management is first of all a difference in the language and the processes. Yeah, project management has a different set of processes to systems engineering, you know, getting a common understanding of the language is important. What we've done at Airbus is we've essentially established a technical management discipline, and that discipline really is the bridge between the two. They're able to speak both the language of systems engineers, and they're also able to speak the language of the project managers. So that's really important. The other thing which is really important is finding a way of getting the project managers engaged as early as possible in the examination of the problem space, because if they come on board at the project start, which is when the scope has been defined, that's already too late. You know, when the scope is defined, you know, you should have the product breakdown structure, the work breakdown structure, the cost breakdown structure, all of those things. And if the project manager hasn't been part and parcel of creating those structures and those plans, then you know, there's going to be a, let's say, a culture shock, and all of the things that should have been done won't have been done. So that again is a big part of what we need to address.
Any additional question from people? Just one question on my side, that is how in the day-to-day, how you see the application of system thinking in our organization? What is your recommendations, you know?
That's really hard.
Yeah, I know.
So do you remember, you've got children, haven't you, Bernardo? Yeah.
Yeah.
So, you know, when they're 3, 4 or 5, they're constantly asking the question, why?
Yeah.
Why? Yeah. So I think we need to ask why more. Yeah. When we're doing stuff, what is the reason for doing this? Why? Yeah. You know, if you ask why a few times, it's very, very powerful. You can really find out, you know, things that you hadn't expected. Yeah. And what you often find is that people are doing things without thinking. You know, they're just following the process, and just following the process is not enough. You need to be thinking while you apply the process, and asking why is really important. Yeah. And then of course you get the what.
You are right. It's curious. We have clever people in our organization, but and never ask why, you know.
Yes.
Always jump to
Yeah.
solution directly.
Yeah.
So I think this is important. I think you are right. System thinking help us to address the whys, you know.
Yeah. Yeah. Yeah, that's one of the pathologies, which is jumping into technological solutions. I've got it here. Yeah. So if it's okay if I just share it for a moment.
Yeah, please.
I'll share. So these when you bring together all of the anti-systemic pathways, you know, jumping to technological conclusions is one of the things that can actually help to promote chaos, yeah, and confusion. Another big one that we fall into is not seeing the connection flow of causality. You know, as engineers, you know, I would say we probably do more thinking. You know, no disrespect to the other disciplines, but we probably do more, let's say, technical thinking than many of the other disciplines. So our natural tendencies tend to be towards this top end, you know, the theory, the technical, and the action. You know, we're very action orientated in engineering. So these pathologies tend to be the ones that we suffer from the most. You know, the firefighting, the resource and energy gap, you know, wasting time and energy. You know, asking why here in this area is really important, you know, so that we don't waste our time and energy, so that we have enough understanding that we don't fall into unintended consequences. And when you ask why, we make sure that we're not going in the wrong direction.
Yeah.
Yeah. So, yeah. So asking why is probably the biggest thing we could do.
Okay. Thank you, Gary, for being here with us, for sharing your thoughts. It's time to wind up our conference. Let me. I would like to leave you with the invitation to be here with us in the next conference. And thank you for all the participants today. And you, Gary, you are part of our community, you know, and thank you for promoting system thinking and system engineering in Spain. I greatly appreciate that, you know.
Yeah, thank you again. I really appreciate the invitation, and my invitation to correspond was very honest. So if people want to contact me and find out more and have more conversations, I'm very happy to do that. And I know that the subject was very rich, and there was a lot of material there. So again, you know, if people want to find out more, then I'm more than happy to talk about it.
Thank you, Gary.